Yep. So for anyone that wasn't here for the partner meeting in November, my name is Kristine Nymoen, and I'm a PhD student at Laurentian University working for Metal Earth. I'm being supervised by David Mole, Phil Thurston, Doug Tenkam, and Jeff Marsh. And today I'm going to present part of some of my research on the Cradle Scale project, which includes isotopic mapping of the Eastern Wawa subprovince. So I would also like to take a moment just to thank my project research and funding partners, both from the industry and the government. So this slide just shows the outline for today's presentation. So I will start with a slight introduction of my project, and then I will move on to show some of the progress that we have on the terrain scale project, which includes some new uranium lead ages. Then I will show you a little bit of how I'm working to build a large scale geochemical and geochronological database to better understand the Archean geodynamics. And to show you how I'm working on that, I'll be presenting some zircon hafnium oxygen isotope data together with some circumtrace element data. And then I will use that to also show some preliminary isotopic maps before I end the presentation in a summary. And I would just like to say that there are preliminary isotopic maps, so they'll probably change from this presentation to next time. So the Cradle Scale project is in the Superior Cradle, and as you might know, this is the Earth's largest Archean cradle, and it has a variety of lithologies, and not just a variety of lithologies, but also when it comes to ages of rocks. So the overall goal for this project is to map the crustal architecture of the Superior Cradle to better understand the geodynamic processes that were active during the formation of this crust. And when we do that, we also want to see what role these processes played in the localization of the many ore deposits that we see. Because, as you know, the Abitibi terrain is one of the world's richest terrains in terms of mineralization. So this rectangle here shows my field area, which is the southeastern Superior Cradle, and it encompasses Eastern Wabigoon, Quetico, Wawa, Abitibi, Pontiac, and Opatica. So the samples that I will show throughout my PhD will be mainly from here. So the previous project, I mean, if you take a step back and look at the overall Cradle Scale project, there has been sampling in this area. My main focus is to do a more detailed sampling. And as you can see from this figure here, there exist over 3,000 uranium lead geochronology samples already. Some are sedimentary detrital zircons, other are metamorphic, and then you have the magmatic and the igneous ones that I am interested in. So what we're trying to do is to image the architecture of the crust. And with that, we try to help identify the controls on location of the mineral systems. So this figure here is from David Mole's paper, and it shows how he has used zircon data to basically make interpretations about how these isotopes can help us in understanding the evolution of the crust, and how also these are related to the many mineral deposits. So my project, as I mentioned previously, is that I am doing a more detailed study. And so what I'm trying to do is that I'm filling in the gaps in both time and space. And this figure here shows the sampling that has been done in the Southeastern Superior by the Metal Earth project. And then with my project, we added some sampling in Wawa in 2019. And then there was done new sampling last summer that then went into the Abitibi, Opatica, and Pontiac subprovinces. And so with the zircon data, I want to incorporate the whole rock geochemistry to study the petrogenesis of the rocks. And in addition to that, we also want to include sulfur isotopes, as this will bring an additional data set and give us like a chance to look at the sulfur sources in the crust. So the progress on the project so far is that I have 160 new samples, and they are from all of these provinces. And so it's a large amount of new data. Some of it is whole rock geochemistry, and then they have uranium, lead, zircon geochronology, then also lutetium, hafnium, and trace elements on zircons, in addition to oxygen isotopes. So what I'm currently working on is samples from the Wawa, those that are shown in the yellow circles. And what I'm trying to do is I'm trying to incorporate the whole rock data with the zircon, uranium, lead, isotopic, and trace element data that I have. And as we're moving on, we will do a bit more sampling in Wawa. As you can see, that is the subprovince that has the lowest density when it comes to sampling. So now I would like to introduce the new uranium lead data, the new ages that I've got from both Eastern Wawa, but also parts from the Quetico, Eastern Wabigoon, and Abitibi. So this first diagram here, just it's very simple. And what I just want to show is where the different samples are populated. So I have 34 samples with an age for the granitoid samples, and then I have 50 new ages for felsic volcanic samples. And what you can see from the diagram is that for the granitoid samples, most of the ages comes from around 2.7. However, there is also an older population back here at around like 2.8, 2.9. So that's interesting. If we look at the felsic volcanic samples, they are slightly older, as we might expect. And so they have a little shift towards the right of the diagram. So these diagrams, again, shows the same information, but here I have split off the samples into the different assemblages. And the reason why I use these assemblages that, is used mostly in the Abitibi is because the data that I have now from Wawa, I will mainly use that in this presentation to compare it to what we have from Abitibi. And so what you can see again is that like most of the granitoid samples plots towards the younger side of the diagram, whereas the felsic volcanic plots towards the older side of the diagram. And worth noticing is also these black columns here. They indicate inheritance. So having introduced the new uranium lead ages, I now want to show some of the zircon data from these samples. And we will have a look at both hafnium and oxygen isotopes and some zircon trace elements. And then I will also show some preliminary isotopic maps. So first here, we're starting with the hafnium isotopes. This diagram here shows the epsilon hafnium value on the y-axis and the age on the x-axis. And then throughout the presentation, you will see that the subprovinces are color-coded, and the outlined squares and triangles are mean values. And then in addition to that, we have some diamond-shaped data points, and those indicate inheritance. Other things that I want to point out here is that this is the chondritic uniform reservoir evolution line. And then we also have the depleted mantle evolution line. And so if we start by looking at just my new data, we can see that most of the samples plots within a range of +3 to +5 epsilon hafnium. But then in addition to that, we also have these older samples plotting back here that has a slight decrease in that range. So that's between +2.5 to +1 epsilon hafnium. They're all positive values. So what we can take out from this is that it seems like we might have two major hafnium reservoirs here. It seems like most of the samples here might show an evolution line that maybe we have a reservoir at 2.9 billion years. And then in addition to that, these older samples seems to be lining up to something around like 3.2 billion years. So then if I put on here a layer with reference data from Moll et al., his 2021 paper, then we can see many more points. And what we can take out from this is that, first of all, like Wawa has these like much older samples, but then also it seems like the Abitibi samples, which are shown here in green, they have like elevated epsilon hafnium values up until around like 2.7, and then they decrease. And we do not see this trend as clear for the Wawa samples. So that suggests the transitioning around like 2.7 billion years. Okay, so we can look at those plots, but it's also interesting to see how they look on isotopic maps, so we can get like that spatial feature. And what this map is showing is basically model ages. And from the diagram, we saw that we might have suggest that we have reservoirs around 2.9 and 3.2 billion years. And so what I've done here is that I've grouped samples around that transition that we saw. So we have the pre-2695 and the post-2695 samples. And here we just see that like the central part of Wawa is mostly dominated by reworked older crustal values. And so the question is like, are those trends real? And I just want to point out that the Wawa area that I'm showing today also has part of Quetico and Eastern Wabigoon, and then also a little bit of Abitibi. But all samples are constrained to that area. So after we look at the model ages, we want to look at the epsilon hafnium values spatially. And so what this map again shows is that there's a domination of chondritic epsilon hafnium values, which is indicative of older reworked crust. And as the same for the last map, there is like no major difference that we can see between the pre and the post 2695 samples when we plot them together. But we know from the plots that it seemed to be like a transition around 2700 or 2695 to be precise. And so we then wonder like if this trend is showing up spatially. And so what we're doing to have a closer look at that is that we construct so-called time slices. So then we can study the area temporally and spatially at the same time. So here are two maps. It shows the older rocks and the younger rocks. What we can see from this epsilon hafnium isotopic map on the left side is that the older rock seems to have like a little bit of a trend here with what seems to be more older crust. And then as we transition over to the younger rocks, we see that, okay, that trend is not shown here, but we do have some interesting, more juvenile stuff that plots to the southwestern part of the eastern Wawa and into Abitibi. So that's something that we want to bear in mind as we move on. Because now we're looking at the zircon-oxygen isotopes. And so what this plot is the delta 18 oxygen values on the y-axis and the age on the x-axis. And again, we have the same legends. And what we see here is that the new data that we now have ages for are mostly plotting in what is the low temperature hydrothermal field. Sorry, not hydrothermal field, low temperature fractionation field. However, these older rocks that we have they seem to be very much spot on in the mantle zircon field. And as we move like to lower values, we enter the high temperature fractionation, which is like the hydrothermal system field. And so one thing that's interesting to look at is that, again, here, we have something happening at 2.7, where it looks like the oxygen data increases in the delta 18 oxygen values. So what we're saying is, okay, there should be like a crustal component there. And again, if we look at that with the reference data, we can see that, like, again, like most of the Wawa samples overlap with the reference data from both Wawa and Abitibi. However, if we just look at like the Wawa versus the Abitibi data, we can see that the Abitibi data is not just only following the trend that we see with Wawa, but it also has samples that are going towards lighter values. So that's an interesting observation. And then again, if we plot this on a map, we can see that most of the new data is in the low temperature field. And so what we can take out from here is that like the central portion here of Wawa seems to have somewhat a little bit lighter values than towards the edges where we have the colder colors. But again, as we saw from the oxygen plot, something is happening around 2700. And so, okay, we want to check that out. And so we will make some new time slices. Again, plotted to the left is the older samples, plotting to the right is the younger samples. And yeah, I want to also just point out that like the older samples here are split into the different assemblages, as I'm interested in seeing if they vary. But what we can see again here for the older samples is that, yeah, they seem to have definitely lighter values. Then if we transition into the younger, we don't see the exact same trend here. It seems like we have heavier values towards the edges. So then if we take a look at some of the circumtrace elements, if we plot delta FMQ on the y-axis against the age, then we can get like some information about the environments here. And if we look at the new sampling and the new samples that I have here, we can see that most of them are plotting, you know, in the oxidized field, and only the really older stuff is plotting like more in the reduced field. And so if we then look at, again, like with some reference data, we see that like, yeah, it's the same trend again. Like we start out with the samples clustering mostly in the oxidized field, but we also have values down in the reduced field. But as we cross around 2.7, or we can see that there is a change again. It seems like although the Wawa and the Abitibi samples are similar, we do see that like both of them, like at 2.7, they trend towards like even more oxidized values. So there is something going on here. If we then take a look at the initial uranium ytterbium ratio plotted against the age, and we can see we have some different fields on this diagram where you have an oceanic source, and then in the middle here you have enriched mantle or a continental source. So it's kind of like a mixed field. And then as we move up, you come into the crustal continental source. And I've included some reference data here as well. So what we can see is that most of my samples, again, they plot in the crustal continental source field. And an interesting feature here is that when we look at the older samples too, they are well within the crustal continental source field. So looking at the reference data, then we can see that, oh, okay, here we do have some differences. The Abitibi shows trends towards actually like down into what is here like the enriched mantle field, but they also do trend all the way down, touching in the oceanic source. This is not something that we really see in the Wawa data, because the rest of the data here seems to be trending towards the crustal field. And after 2.7, the values elevate again. So if we use the initial uranium-ytterbium ratio and plot it against the niobium-ytterbium ratio, then we can say something about like the tectonic setting. I'm not going to make too much of an interpretation here, but what I want to point out is that my data, which is now we're looking at the older assemblages, they're pretty much constrained into this continental arc field of the diagram. But if I plot the reference points here, then you can see that like a lot of the data points are actually trending towards and within the mantle circumary. So that's an interesting observation, because that's not something that I see in my data set. And so if we look at then the younger populations, which is the Temiskaming and the Porcupine assemblages, then like my data is plotting pretty much in the same field as the reference data. It's still pretty much in the continental arc field, away from the mantle circumary. And what we can see, the biggest change from the older assemblages and the younger assemblages is that now we don't really have anything that plots towards the mantle circumary. So whatever that mantle array type magmatism that we showed in last diagram is no longer shown when we go to the younger samples. So yeah, to just sum it up here, the new uranium lead data confirmed that we have older granitoid rocks in the Wawa subprovince that we don't see in the Abitibi. And then from this data set, it looks like the Abitibi and Wawa rocks shows a large degree of similarities in the zircon isotope and geochemistry data. However, there are differences, and those differences are very important now when we go on and try to resolve the question of why the Abitibi subprovince is so much richer in the mineralization. And so the next step here will be to compile all this zircon data, finalize the interpretations, and then incorporate it with the whole rock geochemistry. And so, yeah, as we're working through here, there's a lot of factors when you're doing like making the isotopic maps that you need to take into consideration. Because when I'm plotting, for example, the samples that are like older than 2.7 billion years, I still have some samples that are all the way back to 2.8. So it's important to be careful and also like always take that into consideration when you read off like the general interpretations or the general results that you get from these isotopic maps. But so far it looks like we are having the same trends as David Moll has suggested. We just need to figure out like what is the differences here. So with that, I just want to say thank you for your attention, and I'll be happy to answer questions.
Excellent. Thank you very much, Kristine. Do we have any questions?
It's a lot of data probably, so.
Keaton's come alive. You got a question?
I just have a question for you, Kristine. As you can imagine, I'm pretty interested in this. I was just curious in some of your, I may have missed this, I had to step out for a second, but in some of your earlier maps, you had a nice, almost looked like it was a vertical difference in the isotopes. I think it was one of your early maps right through the middle of the belt, which sort of was reflected on a lot of the maps. You can sort of see it in that one, but if you keep going back, I think there was
I think you can, yeah.
Yeah, I'm curious what happens when you plot things like gold occurrences or base metal occurrences or intrusions on that map. Do they line up with that vertical anomaly?
That's actually a very good question. I actually have not come to that step where I've had the ability to plot those things yet. So I cannot like answer that with any confidence. But yeah, that's definitely something that is interesting as I'm moving on with my research. So
Cool.
yeah.
Thanks.
Yeah, Kristine, John Eyre. I'm just interested in your porcupine and Temiskaming samples. Are those all sedimentary, or do they have some igneous rocks included in that as well?
So the porcupine and the Temiskaming samples that I have from my samples are all TTG rocks. So granitoids. I don't have any sedimentary rocks.
Okay, good. No, I just was curious about that. Thanks.
Yeah.
Yes, I think that's it.
Have you thought of looking at the Archean lamprophirs at Wawa for a direct sample of the mantle at that time?
I have not. Actually, these new ages that I got, like I haven't had that much time to look at them yet. But we're actually going out to sample again in the Wawa this season. So that's interesting.
Okay, thank you very much, Kristine. It's great progress.